more intimately tied to electronic devices now than ever before. Our phones keep us connected whether we're on the go or at home doing our schoolwork, and the global energy crisis is shifting demand in other industries to electronic alternatives. This means that storing electrical energy in batteries is critical for our modern society. But have you ever thought about the chemistry of what makes that possible? What elements would make great batteries for electronic devices, and why? Of course, the answer has to do with electrons and periodic trends of the elements. So let's talk about the properties of the elements in the periodic table. We've already defined effective nuclear charge, which is such a critical thing to understand to help us understand how these elements behave. Now, that's actually how the periodic table of the elements was developed. It was by Dmitry Mendeleev, who really, in what is a conceptually very simple idea, simply experimented with all of the different compounds that had the different elements that was known at the time, and their properties turned out to be periodic. In other words, they repeated. So he would have found that elements like lithium behaved an awful lot like elements like sodium and potassium. And so all you really need to do is list those elements one on top of the other and arrange those in a table, and as you go to heavier and heavier elements, you get things like neon, which are very inert, and then when you go to yet a heavier element, you get things like sodium that you discover, hey, this behaves like lithium. And so you start placing it underneath lithium, and that's when you get this repeating pattern. And remember, a repeating pattern is a periodic pattern, hence the name periodic table of the elements. Now, we've already discussed effective nuclear charge, which is a critical thing to understand here. What we discovered was that the effective nuclear charge of magnesium was not quite as high as the effective nuclear charge of aluminum. And that's because we added a proton, which obviously attracts all of the electrons in the system. But the new electron that we added, right, because we're thinking about neutral elements, we go from neutral magnesium to neutral aluminum. We have an extra proton and an extra electron, but the electron doesn't completely shield the other outermost electrons. So it's a full proton charge, but not a full amount of shielding from the extra electron. So the net effect there is that those outermost electrons are more strongly bound to aluminum. And that pattern is going to continue as we move farther and farther to the right. In other words, effective nuclear charge increases to the right of the periodic table. And so this means that sodium will have the smallest effective nuclear charge, while argon will have the largest effective nuclear charge. So what impact will that have on the periodic table? What impact will that have on properties of the elements? Well, one other thing I want you to consider is what is the change as we go up and down the periodic table? If you calculate the effective nuclear charge for sodium, which you now know how to do, and you calculate the effective nuclear charge for potassium, which again you know how to do, you'll find that they're about the same. In other words, effective nuclear charge doesn't change so much as we go up and down the periodic table. It really changes as we go to the right. So let's think about those effects and try to imagine properties of elements in the periodic table. All right, so the first thing I want you to think about is size. Atomic size. How much space do you think these atoms are going to take up? And how does the amount of space that they take up change as we look through the periodic table? Now, the first thing to think about is the trend in effective nuclear charge. Again, we know that as we go from left to right across the periodic table, effective nuclear charge increases. So how might that affect how much space the electrons occupy? Well, think about it this way. If aluminum has a bigger effective nuclear charge, then that means its outermost electrons are more strongly bound to the nucleus. And if they're more strongly bound to the nucleus, wouldn't they be drawn in tighter? In other words, if we have our diagram that we were considering before, this schematic energy, or not energy, but radius diagram of the n equals 1 zone, the n equals 2 zone, and the n equals 3 zone, what happens is if I add more protons to this nucleus, as I've done when I go from magnesium to aluminum, I increase the ability of this nucleus to draw in the electrons from all the zones, right? They're more attracted to that nucleus, and therefore all of these spatial zones, the n equals 3, the n equals 2, the n equals 1, get drawn in tighter to that nucleus. That is the effect of a larger effective nuclear charge. Therefore, as I go from left to right on the periodic table, my elements get smaller. They really do. They get smaller as we go from left to right. This is a common source of confusion for students because they think, well, argon has more stuff in it than sodium does. It's got 18 protons relative to the 11 that sodium has. It's got 18 electrons. Isn't it bigger? No. The answer is that it isn't at all. It's significantly smaller than sodium, because of this effective nuclear charge effect, okay? So atomic size gets smaller as we go from left to right. So if we want to indicate where size gets bigger, okay, so atomic size gets bigger as we go from right to left. So the elements on the left are bigger than the elements on the right. But what about as we go up and down the periodic table? Effective nuclear charge doesn't tell us so much about this because, of course, we know that effective nuclear charge doesn't change so much as we go up and down the periodic table. But we know from our discussions of orbitals that the orbitals of the n equals 4 level are much bigger than the orbitals of the n equals 3 level, and the orbitals of the n equals 3 level are much bigger than the n equals 2 level, so on and so forth. And we also know from the connections that we were drawing between the periodic table and the orbital structure, i.e. it's exactly the same, p block, d block, S block, right? F block. The periodic table is born out of the orbital structure of matter. So we know that they're intimately connected. So as we go to a new row in the periodic table, we must also go to a new set of orbitals, a new principal quantum number, and those orbitals are most definitely bigger than the orbitals of the previous quantum number. So as I break into the n equals 4 zone here, I certainly expect those outermost electrons, right, in potassium, to occupy a much larger volume of space than the outermost electrons in sodium, based on logical arguments about electrons clamoring to get close to the nucleus, and as I add more and more electrons, they are forced into higher and higher energy orbitals, which are larger in space. So size, as we already know, gets larger as we go left to right, but it also gets larger as we go top to bottom. Okay, for reasons that I think make intuitive sense. And so those are the patterns and the trends, if you will, in atomic size. Now, here is an image that shows us actually measured atomic sizes for elements, and you can see by far and away the trend is generally upheld. As we go from left in the periodic table to right, we see those sizes get smaller and smaller and smaller. Generally also true with the transition elements. Of course, there are a few exceptions every once in a while, and sometimes those exceptions are in places like the D5, right? But generally speaking, atomic size gets smaller from left to right and gets smaller from bottom to top. And the other way to say that is, of course, that elements get larger right to left and get larger top to bottom. All right, so now that we know how big we can expect an atom to be based on simple arguments like effective nuclear charge and position in the periodic table, I want to talk about something called ionization energy. Ionization energy is really a simple concept. It's the notion of how much energy does it take to remove an electron from a chemical element. Okay, so suppose I have some generic element X. What I really want to do is make it X plus. I want to pull away an electron, separate it from its electron, and the energy it costs to do that we call the ionization energy, or IE. And so I think we can come up with some rational arguments of what we might expect the ionization energy to be, or at least trends in what we expect the ionization energy to be, based on the same arguments about effective nuclear charge as we've discussed before. So let's not forget that we know that effective nuclear charge increases as we go left to right. And we also know that size decreases as we go left to right. So doesn't that mean that those outermost electrons, which are of course the ones you would lose if you had to lose an electron, it's going to be the outermost one that gets removed from you. Isn't it true that the outermost electron is more tightly bound in the case of argon than it is in the case of sodium? And if that's true, then wouldn't you expect that electron to be more difficult to remove, for argon with respect to sodium? And you would be exactly right. The periodic trend in ionization energy, in other words, how much energy does it take to remove an electron, increases as we go left to right. It is more difficult to remove an electron from argon than it is to remove an electron from sodium. So let's think about the up and down direction now. So for example, we expect it to be easier to remove an electron from potassium or from sodium. Again, effective nuclear charge doesn't necessarily tell us the answer to this question because, as we know, effective nuclear charge can be very similar, in fact, identical from sodium to potassium. So we have to think about both effective nuclear charge, but also size, which we've just talked about. So think about it this way. The outermost electron in a sodium atom is bound to the protons by a certain effective nuclear charge, okay? And those outermost electrons are also a certain distance from the element. So if I draw sort of a schematic here, let's say that in the sodium atom, I've got some spatial zones. Again, these schematics are a little bit childlike, but nonetheless, they can still help us tell that story. For sodium, my outermost electrons are in that n equals 3 level, okay? Now, as I go to potassium, my outermost electrons are farther out. We know that from the arguments of atomic size. So my outermost electrons are farther away from the nucleus. But what is my effective nuclear charge? It's about the same. So if I have a effective nuclear charge, so imagine I am a sodium outermost electron and I am attracted to that nucleus as though it were a charge of, say, 2.2, which is the effective nuclear charge for that outermost electron. Let's compare that to the outermost electron in potassium, where I am also bound to that nucleus as though it were a charge of 2.2. Same charge, same effective nuclear charge, but greater distance. This electron is farther away from that nucleus and is being drawn to the nucleus with the same effective nuclear charge. I would want a larger effective nuclear charge to hold that electron in place, given that it's so far away. But I don't. I don't have a larger effective nuclear charge. In other words, this outermost electron in potassium is more easily lost than the outermost electron in sodium. And it's more easily lost because even though the effective nuclear charge is the same, the distance is much greater. So that proton has a more difficult time holding those far out electrons that as you go down the periodic table, those electrons are getting farther and farther away. And so even though the effective nuclear charge is similar, the distance is greater and therefore the force of attraction is less. And so what that means is that my ionization energy, in other words, the amount of energy it costs to remove the electron, actually increases in the up direction, right? It costs more energy to remove the outermost electron from sodium than it does from potassium. And these are based on the combination of both effective nuclear charge, which we've talked about, and of size. And when you put those two things together, you get this realization. So ionization energy increases as you go up the periodic table and increases as you go left to right. All right, now what I'm showing you here is a plot, and the plot is of something called the first ionization energy. Now we've talked about that previously, though we didn't give it the label first ionization energy. Ionization energy, as we know, we called it IE, so this is the amount of energy it takes to remove an electron. And first ionization energy, we typically give the subscript 1, and it reminds us that it's the amount of energy it costs to remove the first electron. Because of course, in principle, we can remove as many electrons as we like. So let's just talk about removing that first electron, which generally for all atoms will be that outermost valence electron. And so that's what this image is meant to summarize for us. We're looking at how much is that ionization energy. So what is the first ionization energy relative to atomic number, Z. Okay, so essentially what we're going to do is look at all the elements of the periodic table, walking up through atomic number and seeing the trend. Now remember, we said that the trend in first ionization energy, which we defined just a moment ago, is that we should expect a higher first ionization energy as we go left to right on the periodic table. So let's see if that's conserved. If I look at probably the most relevant row here, we can start at the first row if we want, and that is from hydrogen to helium. And there's that row right there. So we definitely do see a sharp increase from hydrogen to helium. Now let's look at lithium to neon, the second row of the periodic table. Certainly we do see that upward trend. It is true that the first ionization energy goes significantly up as we go from lithium to neon. The trick here, though, is that there's actually some breaks in the trend, right? If we traced our line through this series of elements in order of Z, we would notice that as we went from lithium to beryllium, that trend is upheld. It certainly is more difficult to remove an electron from beryllium than it is from lithium. If we look at the next element, this would be boron. It's actually an anomaly. I suppose I'd call that anomaly. It's not going along with the trend. We would expect everything to go straight up. So generally speaking, it does, but there's a break in the trend here at boron. Likewise, there's another break in the trend up here too. And so if we count through, we go boron, then carbon, then nitrogen, and oxygen. So it seems like boron and oxygen are breaking our trend here for some reason. And so if I filled in the other labels just so that we can keep things straight, there's my carbon, there's my nitrogen, there's my fluorine. We can clearly see here that the issue seems to be with this nitrogen-oxygen pair breaking the trend, and with this, boron-beryllium pair breaking the trend as well. But generally speaking, we see that upward trend as we go left to right across the periodic table. And this trend we can see conserved for all of the other rows of the periodic table. We start low, we end up higher. Now, there are more breaks, and actually those breaks in the trend look like they might be consistent. If I look at the third row and trace my line, again, I see that break again at the third element. If I continue along, I see that break again at the same spot here, right? Just underneath oxygen, we've got sulfur, and there we go, another break in the trend. But generally speaking, we see the trend is upheld. We go, as we go left to right across the periodic table, we do increase the amount of energy it costs to pull an electron off. So this trend is conserved, but there is this issue here that we're going to need to address. Now, the other thing that we thought about when we looked at our periodic table was that the first ionization energy increased as I went up the periodic table. In other words, it was generally thought of to be more difficult to remove an electron from sodium than it is from potassium. So is that upheld? Let's zoom out and take a look. If we trace our lines through all of those S1 elements, we can see that generally that is upheld. In other words, it's a very shallow line, but it does get easier to remove electrons as I go from something like lithium to sodium to potassium, and so that's true. So generally we see all of these elements trending downward as we go to the larger Z, which makes sense because the bigger elements have electrons that are farther away from the nucleus and therefore easier to pull off. And so generally speaking, we see all these trends upheld. What I'd like to do now is think about these breaks in the trend. What's going on in these particular cases? That deserves some discussion all on its own. All right, so what's going on with these breaks in the trend here? We thought about ionization energy, and we said that it should be more difficult to remove an electron from an element that's further to the right in the periodic table. And this is fundamentally due to the effective nuclear charge being stronger. But we've noticed here that when you experimentally measure these numbers, you don't always discover that. So let's take a deeper look at some of these so-called anomalies. At beryllium to boron, we see a break in the trend. And so what I want to do is draw your attention to the electron configuration for both of these elements. Beryllium has this 1s2, 2s2 configuration. Okay? And let's contrast that with boron. The only difference is this extra electron in that 2p zone. So if I need to think about maybe what's going on here, the picture maybe isn't fully clear, but what is interesting is that I noticed that beryllium has one of these configurations that has all of the orbitals in the system completely filled, whereas boron has this extra lone electron in a set of 2p orbitals. So even though the effective nuclear charge for boron definitely would be higher than the effective nuclear charge for beryllium, and those arguments about ionization energy, we would expect boron to be higher, beryllium to me potentially looks like a special case because it's got all of its orbitals completely filled. In other words, one explanation for this is perhaps beryllium is anomalously high. Perhaps it's not boron that's the issue here. Perhaps beryllium is higher than we would have expected because it's got a fully filled 2s orbitals. In fact, all of its orbitals are fully filled. And we had mentioned in a previous lecture, you can recall that we said that orbitals that were fully filled, or at least all half-filled, in other words, symmetrical, seem to impart some sort of special stability. This is a good thing from an energetic perspective. So what we're proposing here is that because of this experimental data, we're actually seeing some experimental evidence, which I promised, for this notion that this fully filled set of orbitals is actually an exceptionally stable thing. And so this added stability, this added, happiness or stability to these electrons cause beryllium to be more difficult to remove an electron from than you might otherwise expect. And it's more difficult to remove an electron from than you would otherwise expect because it's got these fully filled orbitals. And now, if you don't believe that, let's zoom out to now think about the nitrogen-oxygen anomaly. Taking a look at the electron configuration for nitrogen, we see that it's 1s2, 2s2, 2p3, right? That's one of those scenarios that looks like this. Remember the high spin states. Contrast that with oxygen, that's a 2p4. So we would have to add another electron here and disrupt what is an otherwise symmetric scenario here. This is a scenario we have all orbitals exactly half full. Right? We brought these arguments up again when we were talking about electron configuration anomalies with things like chromium, what normally would have been D4, but we made it a D5 because we wanted to make all those d orbitals equally half full. And the argument that we made at that time was that that would be an energetically stable thing to do. And here is evidence for that. Nitrogen here is anomalously high because these 3 electrons placed in those 3 orbitals imparts this stability. It is energetically stable to have all of your electrons represented in an equivalent way. In other words, to have all of your orbitals symmetrical, in this case, half full. So the idea here is that nitrogen is the anomaly, not oxygen. Nitrogen is anomalously high because its configuration is anomalously stable. It's got that extra stability associated with the fact that we've got a symmetrical set of orbitals. All the orbitals are exactly half full. And so it's more difficult to remove an electron from this system because it's exceptionally stable. Now, when I say exceptionally stable, I don't mean more than fluorine, for example. I just mean somewhat more than you would otherwise expect. You get a little bit of boost in stability. And this was exactly what was going on with our chromium case. Those d orbitals got a little bit of a boost in stability by making sure that all of the orbitals were half filled, and that's why that was a better thing to do than leave it as a d4 case. So this is that extra evidence I promised, and it also explains why the breaks in the trend in the other rows of the periodic table occur in exactly the same place. Now, subsequent rows have lots of D's and sometimes F's included in their representations here on this diagram, but suffice to say, now we both understand the trend in first ionization energy, which is exemplified here. We also understand why there would be certain anomalies that are present, and also why that is actual evidence that helps us understand what was before anomalous electron configurations with things like chromium and copper in the D level. This is the evidence we need to help us explain those cases, and that really sort of sums up our discussion of first ionization energy. All right, so first ionization energy is one thing, but we mentioned before that we have the choice to remove more than one electron if we wanted to. And if that's going to teach us something about properties of elements, then that's a useful thing to do. So if I've got first ionization energy, I'm taking one electron away. We've already seen that trend. Harder to remove an electron from elements to the right, harder to remove an electron from elements at the top. But what about a second electron? Let's think about something like lithium. We'll erase these lines and imagine I wanted to remove an electron from lithium. Well, lithium has, as you will recall, an electron configuration that is 1s2, 2s1. So if I want to remove an electron from lithium, that's the one that's going to get removed. So my lithium ion, in other words, my lithium plus, my lithium cation, will have an electron configuration that is 1s2. Now, we would say at that point that it is isoelectronic with helium. And I can quickly visualize that by simply counting backwards through the periodic table. So if I remove an electron from lithium, I count back from element 3 to element 2, and I say, oh, it's isoelectronic with helium, which we can confirm relatively simply by writing out the electron configuration for helium, which is, of course, simply 1s2. And lo and behold, we see that they're the same. Now, ask ourselves, how easy should it be to now remove an electron, a second electron, from lithium plus? Well, there's a couple of different factors at play here. First of all, removing a second electron will always be more difficult than removing the first electron. Why is it? It's because you've got exactly the same number of protons you always had, but now you have one less electron in the system to provide shielding from that nucleus. So for sure, there's going to be a much higher effective nuclear charge for these cations. And so we always know that our second electron is more difficult to remove than our first. And our third is more difficult to remove than our second, and so on and so forth. Always more difficult to remove the next subsequent electron. But there's a second effect at play here too. Notice that after I've removed that first electron from lithium, I'm isoelectronic with helium. And helium's got a full 1s orbital. Now, we just finished a discussion about how especially stable these full orbitals are. This is why the noble gases are so chemically inert. They're chemically inert because each of them, all of them from top to bottom, represent the completion or the fully filled set of orbitals, regardless of the type of orbitals you've got. Whether you've got S's, just S's, or S's and P's, or S's, P's, and D's, or even including the F's all the way down there in radon. It doesn't matter. This is the end of the line, so to speak, for every row of the periodic table, and they all represent systems with fully filled orbitals. And this is why the noble gases are inert. They don't react because they're exceptionally stable. There's no driving force for them to react. They're already stable as they are. And so we know that about helium, but now we also know that about lithium plus. And this is a compounding effect. Not only does it have an especially stable electron configuration now, which it does, but in addition, it's got extra protons relative to helium. Helium, of course, only with 2 protons, lithium having 3. So I would expect the lithium plus ion to be even more difficult to remove an electron from than helium. So our second ionization energy is always more difficult than our first. Our third ionization energy is always more difficult than our second, so on and so forth. And when we remove enough electrons to make us isoelectronic with one of these noble gases, we create a perfect storm, if you will, of not only having a high ionization energy simply because I'm positively charged, but an extra high ionization energy because I've become isoelectronic with a noble gas. So an additional comparison would be, say, magnesium. If I take 1 electron away from magnesium, I expect that to, be as difficult as it is. If I want to take a second electron away from magnesium, it will now be isoelectronic with neon. But it will be isoelectronic with neon with 2 additional protons relative to neon. So I would expect that taking a third electron away from a magnesium 2 plus ion would be an exceptionally difficult thing to do. And I can prove it. We can do experiments that show the ionization energy for all of these different elements. And I'm listing those in the following table. So you can see ionization energy 1, right there in our table, but you can also see ionization energy 2 and 3 and 4 and 5 for elements that have that many electrons. Notice for lithium, we can take the first electron away and it doesn't cost so much energy. But if we take the second electron away, it's more than 14 times as difficult, right? So the second electron removing from lithium is exceptionally difficult. Let's compare, say, boron. First, let's look at the periodic table. And if we have boron, we would expect to be able to take 1 electron away to make it isoelectronic with beryllium, 2 electrons to make it isoelectronic with lithium, and 3 electrons to make it isoelectronic with helium. That means that taking the 4th electron away from boron would be exceptionally difficult if our ideas hold water. And so here we look at this row. Yes, the first electron from boron, a little bit more difficult than the others due to Slater's rules. Second electron, definitely more difficult than taking away the first electron. Third electron, more difficult still. This is in exact agreement with our ideas so far. But look at that 4th electron. The 4th electron is off the charts relative to the 3rd one. There is a huge jump in ionization energy as I go from IE3 to IE4. Explained exactly using the logic of saying that this state, when I take 3 electrons away from boron, is isoelectronic with a noble gas. And so not only is it difficult to take 4 electrons anyway, but it's especially difficult because of that especially stable configuration. This is yet more evidence, if you needed it, that fully filled orbitals are an exceptionally stable configuration of electrons around a nucleus. And this table tells that story over and over again. Every time you go from a species that is isoelectronic with a noble gas and you take yet another electron away, you notice a giant penalty, much more significant jump in ionization energy as you do that. And again, on down the periodic table, this trend is conserved. So we know what an ionization energy is, but we also know what subsequent ionization energies are, which tell us deeper information about these elements, but also confirms yet again more evidence about this orbital structure of chemistry and the stability that's imparted as a result of orbitals being full. So electronegativity, this is a term that you've probably heard before, certainly something that would have been introduced in high school, but what is it exactly? We're looking at another periodic table. This is a version with electronegativity printed directly on it. So if we zoom in a little bit, you can see numbers written next to or underneath every one of these elements, and these are numbers that are electronegativities. So these are measures of this property called electronegativity. So what is it? Well, electronegativity is a measure of the ability of an element to draw an electron toward itself. All right, so think about what that means. If I'm an element that is essentially an electron-greedy element, if I pull electrons toward myself, I am said to be electronegative. And this periodic table is color-coded according to electronegativity. Now, where did these numbers come from? This periodic table is showing you numbers that are on what's called the Pauling scale of electronegativity. And that brings me to my first, I suppose, important point, which is that you have to define what you mean by an element being able to draw electrons toward itself. What does that actually mean? In what context could we actually measure that? And there are different ways. In fact, here at the University of Prince Edward Island, we've developed our own unique way to define electronegativity, which has to do with how electrons are spread out in bonds between certain atoms. If electrons are primarily drawn toward one of those atoms, we say that that atom is more electronegative. But the Pauling scale tends to be the one that's used more often, although it will tell you a very similar thing, and that is that elements to the right of the periodic table are more electronegative. Now, this should absolutely make sense to us because we know, based on arguments of Slater's rules, there we go again with effective nuclear charge, elements to the right of the periodic table have a much stronger effective nuclear charge. Therefore, electrons are drawn in closer. And that would mean that these elements are more electron greedy. If they're bonded with neighbors, they will be more greedy with the electrons that are shared between those neighbors, and therefore we call them more electronegative. But there is an additional point we have to think about, and that is, yet again, the orbital structure of matter. Don't forget about orbitals. If we are looking at the periodic table, ordered by electronegativity, let's pick on fluorine for the moment. It's the most electronegative element in the periodic table, and on the Pauling scale, it's got an electronegativity of 3.98, very large. If we remember where fluorine is in the periodic table, it's right here. Now, if we think about the orbital structure of matter, we see that its valence electrons are 2p5. So it would have electrons filled all the way up into the 2p level, but there would be 5 electrons in here. And let's not forget that the 2p orbital can contain 6 electrons, so there would be a vacancy. There would be a hole left where an electron could go. So this is another one of those perfect storms where I am an element that is very electron greedy with a very large effective nuclear charge and a vacancy and a place for an additional electron to go. When you put those factors together, you get a very high electronegativity. You get an element that is very able to draw electrons toward itself. And that is the fundamental difference why we say that neon isn't at all electronegative, even though it's got a greater effective nuclear charge. Back to the orbital model. Neon has all of these orbitals full, and so it is already satisfied. It has a great effective nuclear charge. All of these electrons are tightly bound, but if it were to draw an additional electron toward itself, the only place for that additional electron to go is in this next available vacant 3s orbital. And that orbital is so far up in energy above the set of 2p orbitals that it isn't energetically feasible to do it. It wouldn't be stable to bring an extra electron onto the neon atom. Even though its protons are, you would think, perfectly capable of holding an extra electron, the electron would have to be in a 3s state, which is too high in energy for that particular element. And so the combination of this orbital model with Slater's rules for effective nuclear charge teaches us about electronegativity. And that is that the trend is generally the same. As you go left to right on the periodic table, you increase electronegativity, except when you've got noble gases that are stable and effectively inert, they aren't electronegative at all. And so that's why we've got fluorine as the maximum in electronegativity on our periodic table. Now, likewise, we know that Slater's rules doesn't change so much up and down the periodic table, but we do know that size does. And these elements down at the bottom of the periodic table are very large. And if they are very large, they are not so able to hold on to those outermost electrons. And if you're not so able to hold on to those outermost electrons, you are certainly not able to hold on to extra ones. So you are decidedly not electronegative if you're down in that bottom left-hand corner of the periodic table. So electronegativity increases as we go up, generally speaking, and as we go to the right, generally speaking. And this takes arguments from effective nuclear charge, size, and the orbital model to help us explain all this. Now, electronegativity is important because we are going to use the concept of electronegativity and these numbers to help us understand how electrons will be distributed in bonded systems. So we haven't even talked about a bond yet, but when we start bonding several atoms together from different points in the periodic table, we can use arguments about electronegativity, which are ultimately explained by orbitals and effective nuclear charge, to help us explain how the electrons will be shared among paired atoms. So in any particular bond, are the electrons spending more of their time on one atom or the other? We can use electronegativity to answer that question. All right, so what does any of this have to do with my cell phone? Right? What are the implications of this to electronic devices and more specifically battery technology? Well, if I want to choose an element on the periodic table that's going to make an excellent battery material, I need it to conduct electricity. I need it to pass electrons along a wire so that I can drive my electronic devices. So I'm going to want an element that is easy to take electrons from. And elements that are easy to take electrons from are over here on the left. And that's from all of the arguments that we've made so far. Electronegativity is minimized, the ionization energy is nice and low, and Slater's rules tells us that the effective nuclear charge is pretty low, so it's easy to pull electrons off of these elements to the left. But which one should I choose? There's still lots to pick from. As we saw in trends in first ionization energies, it's actually a little easier to pull off electrons from elements in the lower part of the periodic table than for lithium. But as we saw in arguments of size, lithium is without question far smaller. And its first ionization energy isn't all that different than the others in the row. So lithium becomes a really, really excellent sweet spot between small size, very light in weight, and easily gives up electrons. So these properties make lithium an incredible source of energy, and it is a ubiquitous component in all battery technologies. Lithium-ion battery technology is certainly here to stay, and lithium is optimal for this purpose because it gives up electrons, it's small, and it's lightweight. Great choice for a battery.